Welcome back everyone. In this lecture actually we will prove the structure theorem for finite abelian P groups. So, first recall what we were doing in the last classes. So, let G be a finite abelian group with the order of G is capital N. Suppose if you write capital N as product of these prime numbers, let us say P1 power alpha 1 etc. PR power alpha r is the prime factorization of capital N. So, then we saw that this G can be written as direct product of this R number of silo P subgroups. So, which corresponds to these distinct primes P1 etc. PR. So, G is exactly equal to G of P1 cross etc. cross G of PR. So, where G of P is defined to be, so those x in G such that order of x divides this P power alpha, or order of x is a power of this prime P, okay, is P power alpha for some alpha greater or equal to 0. Okay, so this is something we proved without using Solo's theorem, but if you use Solo's theorem then it is clear that this G of P for P divides R of G. So, this is Silo P subgroup. So, this is basically Silo P subgroup. So, now G is direct product of these Silo P subgroups. Of course, all of them are abelian. So, in particularly if you are interested in proving the structure theorem for general finite abelian groups, so then we can reduce the problem to finite P groups, okay, for given prime P. So, that is what we are going to assume now. So, we just assume from now on G is just a finite P group, okay. So, let G be a finite P group where P is a prime, okay. So, that means the order of G is indeed P power alpha for some alpha greater than or equal to 1. Okay. So, P is indeed prime number. So, P is a prime number. So, now what we want to climb? So, we want to climb, this is the main theorem. So, the theorem G can be written as direct product of cyclic groups, okay. Of course, they are all subgroups of this G. So, it must have some the cardinality of those cyclic groups will be prime power. So, P power some E for some E, okay. So, what we want to prove? So, we want to say that G is isomorphic to, so I just write it as equality. So, this is G modulo some P power E1 Z cross etc. cross Z modulo P power some ET Z, where you can choose these exponents such a way that you arrange them in the decreasing order. So, then this E1 etc. ET, this form a partition of this alpha, okay. So, this is indeed a partition. So, that means this E1 is greater than or equal to etc. greater than or equal to ET, where ET is greater than or equal to 1, and the sum of all these exponents E1 plus etc. ET, this is exactly equal to alpha. That is the meaning of this is a partition of alpha. So, this is our claim, okay. So, we also want to prove moreover these exponents or the partition that is uniquely determined by actually this group G, okay. So, moreover this partition E1 etc. ET of alpha is uniquely determined by G, okay. So, this is what we want to prove. Okay. So, before proving this we need some preparatory results. So, we need to understand how to choose this exponent E1 first, then by induction we choose all other exponents, okay. So, for that purpose we already defined what is called the exponent of G, okay. What is the exponent of G? let's recall, exponent of G is nothing but maximum of all possible order of the elements of G. So, you take maximum of order of x in G, that is called the exponent of G. Since G is finite, this exists. So, now if you call this exponent, okay, let us call it gamma. So, then what happens? So, here this group that you have already started with, you can see that if it is isomorphic to z modulo p power e1 z cross etc. z modulo p e power t z. So, then you can see that the exponent of the right hand direct product must be e1, because e1 is greater than or equal to et. Okay. So, all other exponents. So, because of that, this e1 p power e1 will be the highest order for the elements of this direct product. Okay. So, now from this it is immediate that this gamma, okay, so if you call order of G equal to p power alpha, then this gamma must be at most alpha from using the Lagrange's theorem. So, note that gamma is less than or equal to alpha. Okay, this just uses the Lagrange's theorem, using Lagrange's theorem. So, now what we want to do, we want to prove that any finite P group is actually direct product of these cyclic groups. Okay. But before that, let us understand one particular type of finite P group, so which is indeed cyclic group. Okay. So, what is the property of this cyclic group? So, if you take z modulo p power alpha z, so this is a finite P group because the order is p power alpha, and this is a cyclic group. So, what property this has? You can see that, so for given any divisor, okay, of this p power alpha, that means p power I for I less than or equal to alpha, we have a subgroup of order p power I. But we also know that there exists unique subgroup of order p power I. So, that is the very special about this group. So, indeed all we need is this has a unique subgroup of order p. Okay. So, this is some interesting property of this cyclic P group. Okay. Now, we will ask this question whether this property indeed characterize this cyclic finite P group. So, indeed that is the case. So, here is the lemma. So, if G is a finite abelian P group and G has a unique subgroup of order P, so then we claim that G must be cyclic. Okay. So, if you have a finite P group that has a unique subgroup of order P, then that must be cyclic. Okay. So, let us prove this statement. So, what we will do? We will actually use induction on the cardinality of G and prove this statement. So, as before, we just assume that the cardinality of G is p power alpha, okay, and alpha is greater than or equal to 1. If alpha is 0, then there is nothing to prove. So, what we will do? We will actually find a nice quotient of this G, and then by induction we say that that also satisfy the hypothesis of the result. So, by induction it must be cyclic. Using that information, we will actually kind of find cyclic generator of G. Okay. So, we know that this has a unique subgroup of order P. So, call that subgroup H. So, H is a subgroup of G such that the order of H is P. Okay. So, now what we can do? We can define this map pi from G to G. So, which takes let us say x to Px or x power P. Okay, so let's use the exponent notation, no issue. So x goes to x power p. So then, because G is abelian, so this must be actually group homomorphism. So pi is a group homomorphism as G is abelian. So that is not a problem. So now look at the kernel. The kernel of pi is going to be those G and G such that G power p is identity. So what does it mean? So kernel of phi consisting of either identity or order p elements. But we know that there is only one subgroup of order p. So if you take any non-identity element from this kernel pi, then the subgroup generated by that should have order p, okay, because G power p is identity. So the order of G where G is non-identity must be p. So that forces that this kernel pi must be coincide with H. There is no other option. So the kernel pi must coincide with H, as H is the only subgroup of order p. So now what we can do, we can actually go modulo this kernel. So then you can see that this G modulo the kernel phi. So this is again a finite p group. So what is the cardinality of this? The cardinality of this is cardinality of G divided by the cardinality of pi, which is p power alpha divided by p, which is p power alpha minus 1. Okay, now if this G modulo kernel pi satisfies our hypothesis, so then we are done. So then we can conclude that by induction G modulo kernel pi is indeed cyclic. Okay, so let us see whether it satisfies the hypothesis. So you have a surjective map G to G modulo the kernel pi, okay, so which is given by this pi. But we have this lattice isomorphism theorem, which says the subgroups of G modulo kernel pi has one-to-one correspondence with subgroups of G that contains the kernel pi. Okay, the subgroups of G containing kernel pi from this set to, so we have one-to-one correspondent to subgroups of G modulo kernel pi. Okay. So now if you have, for example, two subgroups, okay, here in this right hand side, so G modulo kernel pi that has, let us say, order p, then if you pull back, then what will happen? So then both of them, like let us call here, okay, let us say H1 tilde, H2 tilde, there are two groups. So both are having order p, let us say. So if you pull back, both they come from this H1, H2, so both contains this kernel pi. Okay, but let us understand what is this G modulo kernel pi. Okay, so because the map is indeed from G to G, so you can see that, so this G modulo kernel pi is indeed isomorphic to the image pi of G. Okay, so the pi of G is isomorphic to G modulo kernel pi, but pi of G is indeed a subgroup of G. Okay, because the pi is a map from G to G. So that means if you have two groups here in the image G modulo kernel pi, so then you can see that those two groups are there in pi of G only, so which is there in G only. So that tells you that you can't have two subgroups of this pi of G that has order p, okay, because then that would imply that G also has two subgroups of order p. Okay, so we don't need to use this lattice isomorphism theorem. So it is immediate that pi of G being a subgroup of G implies that pi of G can have at most one subgroup of order P. Okay. So, can have at most one subgroup of order P. Now, P divides pi of G. So, by Cauchy's theorem it must have subgroup of order P. So, in particularly kernel pi is also actually, so that H is indeed sitting inside this pi of G. Okay. So, even though the kernel H is the kernel, but still it is sitting in that image. Anyway, so pi of G satisfies our hypothesis. The cardinality of pi of G is same as the cardinality of G modulo kernel pi, which is p power alpha minus 1, and it satisfies our hypothesis. So, it must be generated by some cyclic element. Okay. So, pi of G must be generated by, let us say, y bar. Okay. So, y bar is, let us call it y power p. Okay, because y bar is just the image, so of y, so that must be y power p. So, now if you take this y inside G, so what could be the order of y? Let us try to compute. First of all, order of y must be some p power gamma, because order of y divides p power alpha, and this gamma must be less than or equal to alpha. Now, note that since y power p generates pi of G, you can see that order of y power p must be p power alpha minus 1. Now, since y power p is exactly having order p power alpha minus 1, that would imply that y has order p power alpha. So, let us check this. So, here is the quick proof. If you take y power p power alpha, this is nothing but y power p power alpha minus 1. So, that means it is identity. So, that means order of y divides p power alpha, that is clear. So, this implies order of y divides p power alpha. So, now if you take y power p power some, okay, let us say this gamma. So, y power p power gamma, so gamma is the order, p power gamma is the order, is identity, then that would imply y power p power gamma minus 1, that is identity. So, that would imply that order of y power p is less than or equal to p power gamma minus 1, but this is p power alpha minus 1. So, this implies that p power alpha minus 1 less than or equal to p power gamma minus 1. But that would imply immediately alpha minus 1 less than or equal to gamma minus 1, that would imply immediately alpha is less than or equal to gamma. So, that means alpha must be equal to gamma. So, that means if you pull back the cyclic generator of this this image pi of G, so then that must be cyclic generator of G. So, we proved that G is generated by this cyclic generator y. Okay, this completes the proof of the lemma. So, basically what this lemma says, if G is a finite P group and G has a unique subgroup of order P, then G must be cyclic. So, now let us use this lemma and then prove our result. Again we are going to use induction on G. So, what is our result? So, our theorem, so before proving the theorem we will actually prove this supplementary result. Okay. So, if G is a finite P group and let us say H is generated by A, where order of A is the exponent of G. So, then there exists K subgroup of G such that G is indeed isomorphic to H cross K. Okay. So, once we prove this, then by induction we can see that G must be isomorphic to product of cyclic groups. So, there is no other option. Okay, let us prove this. So, how one can prove this? One again uses induction. Okay. But anyway, so now let's start with group G. Let's say the order of the group is p power alpha, and then exponent of G is just say p power some gamma, where 0 less than or equal to gamma less than, okay. So because G is, let's say, non-trivial, so this gamma must be at least 1. So then this is less than or equal to alpha. So now what is the case 1? Case 1 is if gamma equal to alpha, then we are done. Why? Because exponent is exactly the order. So that means there is an element of that exponent of G, which is the order of G. So then in this case G must be cyclic. So the G must be cyclic. So then we can assume that gamma is indeed smaller than alpha. Okay. So then we know that this H that we have chosen is indeed proper subgroup of G, okay, because this is having exponent exactly, order of A is exponent of G. So the H cannot meet the order of G. So now you can see that G is not cyclic, okay, G is not cyclic. So from our previous lemma, okay, from the previous lemma, we get another group, call it L, subgroup of G, such that order of L is P and L intersection H will be trivial. So why such subgroup exists? So this H is already a cyclic subgroup of G. So since order of this H is order of A, which is exponent of G, which is p power gamma, gamma is greater than or equal to 1. So this must contain a subgroup of order P. Okay. So this H already contains a subgroup of order P. Okay. So now since G is not cyclic, it must contain another subgroup of order P. Okay. So we can very well choose, because that another subgroup cannot be inside H, because this is contains a subgroup of order P and a unique subgroup of order P. So that means we can choose L from G, and that also has order P, and L intersection H is trivial. Okay. So now one can look at this quotient map from G to G modulo L, because all the subgroups are normal. One can talk about G modulo L, no problem. So you have this surjective group homomorphism. So this is group surjective group homomorphism. Okay. So now you have this G mod L. What is the cardinality of G mod L? The cardinality of G mod L will be cardinality of G divided by cardinality of L, which is p power alpha minus 1. So this is again a P group. Okay. So now you can assume that so this is indeed product of cyclic groups. Okay. But what we are looking at, some subgroup of G, okay, which is K, which is isomorphic to this okay, not exactly. So this is again the complement of this H. So that is what we are looking at. Okay. So we can use induction, and then we need to cook up something here using the data. So let's see like what we are going to do. So we have to understand first of all, so what is the induction? So the induction about getting the complement subgroup for this H. Okay. So what is H? H is cyclic subgroup generated by a cyclic generator, which has order exactly exponent of G. So if you are able to produce an element which has order exponent of G, and then take the subgroup generated by that element, then for that subgroup you have complement, that is your induction hypothesis. Okay. So let us try to do that here. So since this pi is a surjective group homomorphism, it is easy to see that the exponent of G is at least exponent of G modulo L, because exponent is nothing but maximum order of x in G. So, you can easily see that for that particular exponent of G. So, you can see that y bar of exponent of G will be trivial for all y bar in G model. So, that actually implies this. Okay. So, I will leave it to you to check. This is very easy thing to check. Okay. So, now you have this exponent of G, which is at least the exponent of G mod L. So, now look at what will be the corresponding subgroup of G mod L that corresponds to H. Okay. So, you have this surjective map pi from G to G mod L, and then the L is chosen such a way that L intersection H is trivial. Okay. Now, you have H here. So, let us look at the image of H inside G mod L. So, it is clear that the pi of H is indeed isomorphic to H plus L modulo L. Okay. So, this will be your pi of H. This is not isomorphic, this is equal. Pi of H is H plus L mod L. So, if you use one of the isomorphism theorems, then it says that this is isomorphic to H modulo H intersection L. So, that is exactly equal to H modulo the trivial. So, that means this is isomorphic to H. So, pi of H is indeed isomorphic to H. That is because L intersection H is trivial. Okay. So, using the isomorphism theorems, you can conclude this. So, now what is the order of H? Order of H is exactly exponent of G, and exponent of G is greater than or equal to exponent of G mod L. Now, note that H is cyclic. Okay. So, H is cyclic. So, that implies pi of H is also cyclic. So, that means by going modulo this L, where L intersection H is trivial, so we are preserving the exponent. So, the exponent of G is same as exponent of G modulo L, and this pi of H is indeed a cyclic group corresponding to exponent of G modulo L. Okay. So, that means, so let us say this is generated by some y bar. Okay. So, for this pi of H, we have the complement subgroup in G modulo L. So, by induction, we can get some k bar inside G mod L such that the G mod L is exactly equal to this pi of H direct sum or the product k bar. Okay. But this k bar should come from some k. So, let us take the k to be pi inverse of k bar, because pi is a map from G to G modulo L. So, you just take this k to be pi inverse of k bar. So, now look at what is happening there. So, you have G, you have this G mod L, you know that this is nothing but pi of H cross k bar, but this is naturally isomorphic to H cross k bar. But the thing is, this k bar is just k modulo L. Okay. So, this is indeed k bar is k modulo L. So, somehow you have to find a complement here in G for H. Okay. So, that should resemble this k bar. So, that is why you take k, which is pi inverse of this k bar. So, now we claim that for this k we have G equal to H cross k. Okay. So, now let us look at what is happening. So, G is going to be definitely H. Okay, let us use the additive notation H plus k plus L. Okay, L. Yeah. as G mod L is equal to H mod H plus L mod L, okay, H plus L mod L plus K mod L. So, since G mod L is H plus L mod L plus K mod L, so you can easily see that G is exactly equal to H plus K plus L. So, now L is subgroup of K. So, that imply that G is exactly H plus K. I am just using additive notation for the group operation, okay. We are in the abelian group, there is no harm. So, now we have that G is indeed H plus K, but if you want to say that G is direct product of H and K, you need to prove that H intersection K must be trivial. Okay. Let us look at what is the H intersection K. So, let us take X inside H intersection K. So, then it is clear that this X bar, okay, which is pi of X, is going to be inside your pi of H intersection pi of K. But what it is? So, this is pi of H intersection pi of K is K bar, but K bar is the complement. So, this is going to be trivial. So, this is E bar. So, that means if you take X, X has to be inside. What is E bar? The inverse image of E bar is pi inverse of E bar. So, that is going to be L. Okay. So, that means X is inside H intersection L, because X is already in H and K. So, now H is in L, that imply X is in H intersection L. But what is H intersection L? If you go back to your choice of L, so L is chosen such a way that H intersection L is trivial. So, that means this X must be trivial. So, that tells you that H intersection K is trivial and G is H plus K. So, that implies that G is isomorphic to H cross K or H direct sum K. Okay. So, this proves that by induction for this cyclic subgroup which has the cardinality exponent of G, you have the complement. So, now by induction you can see that, okay, if G is isomorphic to some X, okay, direct sum K, where R of X is exponent of G. So, now use induction on the cardinality of the group. Okay. So, then you can see that this K will be isomorphic to some G modulo P power E2 Z direct sum etc. direct sum G modulo P power E t Z. Okay. So, now if you put them together, you can see that the cardinal this order of X is P power E1, which is the exponent. So, you can see that this is going to be P power E1. So, G is isomorphic to Z modulo P power E1 Z cross etc. cross Z modulo P power E t Z. So, I am mixing up notation, maybe direct sum and direct product are same in the abelian case, no issue. Okay. So, this proves G is direct product of these abelian cyclic groups which has prime power order P power some E1 etc. Et. Okay. So, this completes the proof for the finite P groups. So, now uniqueness is also somewhat clear. Okay. So, if you start with general group G, we already seen that G can be written as some GP1 cross etc. GPT. Okay. So, let us say cardinality of G is n, where n is written as P1 power alpha 1 etc. Pt power alpha t. Then the each of this GP is given to be those X in G such that the order of X is P power alpha for all, some alpha greater than or equal to 0. Okay. So, from this you can see that this g of p is uniquely determined by the choice of that prime p. Okay. So, the collection g of p1 etc. g of pk. So, being they are silo p subgroups, since g is abelian. So, they are all normal. So, they are unique silo p subgroups. So, because of that they are uniquely determined by g. So, they are uniquely determined by g. So, now if you focus only on the particular g of p, so then we know that this g of p is written as z modulo p power e1 z cross etc. cross z modulo p power et z. So, now what we can do, we want to claim that this partition e1 etc. et of let us say this alpha, where cardinality of gp is p power alpha. So, this is uniquely determined by g of p. So, how one can get this? So, you can simply look at this p times gp. What is this p times gp? This is just this x power p x in g. So, this is that subgroup, the image of x goes to x power p. So, then I will leave it you to check, it is easy exercise, that if g of p is isomorphic to this z modulo p power e1 z etc. z modulo p t z. So, then this p g of p will be naturally isomorphic to z modulo p power e1 minus z cross etc. cross z p power et minus 1 z. Okay. So, then in case if you have two different partition that corresponds to the same group, so then what will happen? Let us call them e1 etc. et. So, this is the first partition of alpha, and the second partition is call it f1 etc. ft dash. So, for this correspondence, let us say g of p is isomorphic to the first one p1 z cross etc. p e t z. Similarly, g of p let us say isomorphic to z modulo p f1 z cross etc. z modulo p power f t dash z. So, then from this you can see that from this observation you can see that p g p. Okay. So, that must be isomorphic to both. Okay. So, in particularly z modulo p e1 power minus 1 z cross etc. cross z modulo p e t minus 1 z must be isomorphic to z modulo p power f1 minus 1 z cross etc. cross z modulo p power f t dash minus 1 z. So, these two things should be isomorphic just by comparing these two and saying that PGP is uniquely determined by GP. So, this immediately implies if you look at this E1 minus 1 etc. ET minus 1. So, this tuple should be exactly equal to the tuple F1 minus 1 etc. FT dash minus 1. But it can so happen that some EI's could be equal to 1. So, only except those things, so these things are equal. Let us say some R number of terms here is 0 and S number of terms here is 0. R terms, S terms are 0. So, that means what? You have E1 minus 1 etc. E R minus 1 minus 1. Okay, let us call it R here and S here. So, we will go up to R here. Okay. Up to this is non-zero, then after that it is all 0. So, that means you have T minus R terms here and then here T minus S terms. So, this is equal to F1 minus 1 etc. Fs minus 1. So, all other terms are 0. So, that means those Fi's Fs plus 1 etc. they are all 1. Okay, they get cancelled. So, here it is T minus S. So, this tuple is equal. So, then from this you can see that at least for up to this R and S. So, first these things are non-zero, all of them are non-zero, and this is also non-zero. So, that tells you that these terms, okay. So, this E1 minus 1 should be equal to F1 minus 1 and so on, and then ER minus 1 should be exactly. So, this R must be equal to S and ER minus 1 should be equal to FR minus 1. So, this says at least for this R terms E1 equal to F1 and so on, ER equal to FR. But note that all these terms are greater than or equal to 2. Whenever they are greater than or equal to 2, by going down to this quotient, we get that corresponding tuples are equal, no issue. Okay. But if you think about it, so we also need to say that this T minus R is same as this T dash minus R. Okay. So, because here it is T dash, so we have to say that T dash minus S and T minus R, both of them should be same. So, how do we say that? For that we can actually compare the order of the group. Okay. So, what is the order of the group? The order of the group is exactly P power alpha, which is obtained by just adding all the exponents E1 plus etc. Et and then P power F1 plus etc. Ft dash. Now, first R term, they are all equal. That means this can be written as like this, P power E1 plus etc. plus ER and then P power the remaining term, that is T minus R, which is exactly equal to P power F1 plus etc. plus FR and then P power T dash minus R. Okay. So, now we know that E1 is same as F1 and then ER equal to FR. So, this term that appears on the both side, they must be same. That means those things can be cancelled, then that would imply that P power T minus R must be same as P power T dash minus R. So, that would imply that T minus R is same as T dash minus R, that would imply that T equal to T dash. So, once T equal to T dash, then the number of ones that appear here or the number of zeros that appear here must be same as number of zeros appearing there. Okay. So, that means the tuple that we have here, okay, not only T equal to T dash, this also proves this partition E1 etc. Et must be same as this F1 etc. Ft. Okay. So, this proves that. So, when you restrict your attention to this P group G of P, which is the silo P group, so then the partition of that you get from that decomposition of G of P into cyclic subgroups. So, that is uniquely determined by G of P, and G of P's are uniquely determined by G because they are determined by indeed the order of the group, okay, that Pi's that are involved. So, this proves that the factorization that you get for G as a product of cyclic prime power order groups, so that must be unique up to a permutation. Okay. So, let me just write the theorem and then I will stop. So, what is the theorem? So, if you put together everything, if G is finite abelian, then G can be written as Z modulo some P1 power E1 Z cross etc. cross Z modulo some PT ET Z, where this E1 etc. sorry P1 E1 etc. PT ET. So, this is a multi tuple. So, the repetitions are included. So, this is uniquely determined by G itself. Okay. So, not only it is isomorphic, moreover, so these tuples that involved in this decomposition, they are uniquely determined by this G. So, this Pi's can repeat, okay, that is also there. So, this P1 etc. Pt, they are primes, so not necessarily distinct. So, this is also part of the result. So, this proof for any finite abelian group we have this very nice cyclic decomposition, okay, and these numbers prime powers, okay, P1, E1 etc. Pt, Et, that is uniquely determined by G. And this decomposition actually called elementary devices decomposition. So, these numbers that are involved, so this P1, E1 etc. Pt, Et, they are called elementary devices. Okay, this completes the proof of the structure theorem of finite abelian group. So, which is actually indeed very important theorem in the first course of group theory. So, with this actually so we are indeed completing the course. Okay. So, I hope you must have enjoyed this course and then learned some amount of group theory from this course. Okay. I hope to meet you soon in some other occasion. Okay, thank you. I will stop here.